thing is denoted with a bold P or a P with a line over it? A vector, yeah. Okay, and if you scale the vectors of a vector field so that they all have the same length, what is that thing called? A direction field. And then you can use a direction field to sketch out the what. And the thing I'm looking for is several solution curves plus the equilibrium solutions. They make up the phase portrait. So yeah, these are misnumbered. That's 13 because I forgot to adjust for having quiz days in there. Okay, so we're just going to start with some notation. We're going to, instead of writing things out as two separate equations, we're going to start writing things as a single equation, but with vector notation. Okay, so instead of writing r prime equals 2r blah, 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 and f prime equals another equation, we're going to use a vector. So bold P is going to represent a vector valued function, right? So bold P contains an r of t and an f of t. You could also write it horizontally if you want to save paper, and your book does that sometimes, particularly like when you're reading the answers because they're trying to save paper. So that means that another way we can define this system of differential equations is as a single equation p prime of t. And we're just writing vectors now. So bold p prime is r prime f prime, and then it's a vector that has two inputs, one for r prime, one for f prime. So for each vector, or you could think of it as a point in the RF plane, RF, you can calculate p prime, which is r prime f prime, that defines a vector. So since the vector is the derivative of p, the vectors are tangents to the solution curve p. And when you plot a bunch of these vectors in the RF plane, you create what's called a vector field. So let's just calculate a few. So I've got some RFs, and I want to calculate the vector that lives at that RF, r prime f prime. So we have the RF plane here. And at every point in the RF plane, I could draw a vector r prime f prime. So pick a random RF, like let's pick 0, 0. It's a real easy one. You calculate r prime f prime by using the equations for r prime and f prime. Okay, so 2r minus 1.2 RF, well, that'd be 0 and 0 when you plug 0 in for r and f into those two. So you just put a point there if there's no, if the vector is 0, 0. And then let's do, say, 1, 1. So that would be 2 minus 1.2 is 0.8. And negative 1 plus 0.9 is negative 0.1. And then you could just pick random ones, like maybe 0, 2. Plugging in 0 for R and 2 for F, I get 0 and then negative 2. So at the point at 1, 1, let's see, I got 0.8, negative 0.1. So 1, 1, I'm going to draw a vector that goes right 0.8 and down negative 0.1. So something like that. And then at 0, 2, I'm going to draw a vector that goes 0 right or left and down negative 2. So it's this long vector that goes like this. And then, I don't know, let's do one more. Let's do, maybe we'll do two more. Let's do 3, 0. Plug 3 in for R and 0 in for F. So I get 6 and 0, 6, 0. So at 3, 0, my vector points 6 in the right direction and 0 up or down. So this is a really long vector over here. And then let's see, I'm going to do one more in the plane that's not on an axis, like maybe 2, 4. So I plug in 2 for R and 4 for F. So I have 4 minus, I need a calculator. Two times 2 minus 1.2 times 2 times 4, negative 5.6. And then negative F, so that would be negative 4 plus 0.9 times 2 times 4, negative 2.4. Okay, so at the point 2,4, I'm going to draw a vector left 5.6, down 2.4. It's going to be a super long vector like this. So this is very tedious and very messy. Okay, it's kind of job that a computer would be good at. Your TI-89 can do it. So can this free software called WinPlot. You can make GeoGebra do it too. And in your next project, you're going to be doing some of this. And I have some little tutorial videos to how to use those pieces of technology to make those vector fields. But aside from that project, I typically won't make you draw these. Like I'll give you one and you're going to use it to answer questions. So here I did a whole bunch more, right? So here are several vectors for that predator-prey system. The arrows tell you that the direction of the solution curve, and the length of the arrows tells you how fast the solution curve is being drawn. That is how fast the R and F populations are changing at that population size. So you could imagine it'd be like trying to drive a car in a big parking lot that's marked with arrows of varying lengths. And the arrows tell you where to go, and the length of the arrow tells you to speed up and slow down. However, having arrows that are all different lengths can get really messy really fast because they start to cross over each other, and some are super long and some are super short. So we usually just scale them all to a uniform size. You lose some information about speed, but the resulting picture is so much easier to read that we're fine with the loss of information. And the result is called a direction field. So here's a direction field that I made. I made these using WinPlot for the predator-prey system that we've been talking about. So this one on the left is just the direction field, and you can see that it's suggesting the location of an equilibrium point here. Like everything seems to be swirling around this point that was our equilibrium. And then there's another one at 0, 0. And I only plotted positive R and F values because they represent population sizes. But in other instances, you might want to look at more of the plane. And then you can see you can kind of just sketch. You can pick an initial condition, like what if I start with 2 rabbits and 1 fox, right? Or maybe it's 2,000 rabbits and 1,000 foxes, whatever the units are. Then once you have your initial condition, you can kind of just follow the slope field and see what happens. The direction field. Follow the direction field. So this is really similar to slope fields. It's just that we're dealing with a system of differential equations now. So we have 2 solutions, a function for rabbits and a function for foxes versus just one solution y. And then when you sketch out several solution curves and plot the equilibrium points, you've made a phase portrait. But don't forget, other than eyeballing where the equilibrium points are, you can find them explicitly by setting your derivatives equal to 0. Okay, so a little note, now that we're working with systems and you have two dependent variables, R and F in this case, you can see why we've been using T as our independent variable all semester. Because then our dependent variables can be X and Y, and then when you plot solution curves, they're in the XY plane. All right, that's it. I'll pass out the quizzes.